you are solving for the absolute velocity, right? So this time, as you have both inertial frame and the non-inertial frame, because it's rotating, okay, so the relative velocity, okay, that determines the behavior of the flow. So here the relative velocity, the divergence of the relative velocity, okay, this is the velocity of the flow, this is the velocity of the blade. So this is supposed to be 0, right? Similarly, the convective acceleration term, okay, that will be again with respect to the relative velocity, right? So again, if you go and expand the uh, expression over here, okay, you will get additional term in your equation, okay, that is the governing equation for sliding mesh or the moving mesh. Okay, you will get a term for centrifugal force, Coriolis force, this kind of thing. Okay, so to model that one, this is something is rotating. So normally we have prepared a cylindrical zone across it. Normally it should be a rotational symmetric kind of thing along a axis. We have created a cylindrical zone out of it. Okay, we do not want the solid to be taken into the solver, because we are not solving any conjugate heat transfer problem. We need only the fluid person. So the solid, we take the cutout from the fluid, so as if it is showing that there is fluid which surrounded that solid blade, that we make it's a an inertial non-inertial frame. So where we will apply the additional term to make it inertial and solve it the whole Navier-Stokes equation, while rest of the domain, okay, we are solving only the Navier-Stokes equation, right? So let's see. Okay, already you have named it group. This is my inlet, this is my outlet, this is my blade profile. Already I have named those things. The only thing yesterday, as I show you, I need to do the share topology. Let's move to the workbench. Okay, let's share. This is showing 3 faces, they need to be shared. I did the share topology, yes. Now it is showing T edges in the blue edges. They are showing the T edges, means it's a share. Okay, now the geometry itself is share, everything is there. So now in the Fluent parallel, go import CAD, pump selected, CFD surface mesh. Minimum is something around 0.5, maximum is something around 5, 1.2 proximity, 1 gap per proximity, import. So now the geometry itself, now the Fluent solver is doing it, converting it to the surface mesh, and it will import it to the Fluent. Okay, it's already imported. Let's see. This is the pump, scaled pump. This is the name that we have already given over here. Let's see. Fit. Yeah. This is the pump that we did it over the space claim. We imported it here. Okay. So to volume mesh it, let's see how much parts are extracted over here. Okay. So first assume if everything is correct, there is some T phase or there is some free phase or something. How to do that? Yesterday I show you. Right click. Okay. Diagnostic, connectivity quality. You check if there is any free phase. No, there is not any free phase. There is any multi phase. No. There is any duplicate? No. There is a self intersection? No. The geometry is okay, right? But it's needs some refinement. Okay. We'll do this refinement and all. I'll show you how to do it. Okay. So let's compute the volumetric region. Okay. We computed the volumetric region. How many volumetric region prepared? Three volumetric region prepared, right? So let's see what are those volumetric region. Okay, reset the view. Okay, let's see what is the first draw. This one is showing which, not this way. Yeah, this one is showing the casing and the fluid domain where we are solving only the Navier-Stokes equation. Okay, this is the person is showing. We can name it something here. Rename it. Change first. Let's change the type to fluid. Okay. Then manage rename. This is something 01. This is the inertial region, right? That is the casing, or make it some convenient name. Casing 01 CASING casing region. So this is the thing. Then let's reset. See what is this region. Okay, this is the blade region. You can see. Okay, this is the if you move on, this is the non-inertial region. Okay, this is the MRF region, which is composed of the solid blade. Right. So this do it. Change type to fluid and manage rename 02. This is the MRF region, or if you are doing the transient analysis, let's do the slide region. Okay, let's see what is this draw. So this is the blade region because it's a closed volume. Although we put it over here in the dead region, automatically the volume is extracted over here. Right? This is the blade profile. We don't need to the blade profile to be meshed here. Volume meshed here the blade profile. What you will do? Because means it's a closed region by the surface, so by default the blade is created over here, but we don't need to volume mesh it because we need the outer profile of the flow. If you look at, this is something around the external flow across the blade that is of interest to us. We don't need any analysis of flow inside the blade because it's a solid region or any. That's why we don't need any mesh in the blade, inner volume mesh in the inner part of the blade. So what do we do? Just select it and change type to dead. Dead means it will not do any volume mesh generation inside the blade, and it will not consider a blade for the what do you call physics purpose, solving any physics. Okay, we put the blade into the dead zone. Now this is a casing, this is a MRF, right? So let's reset and say it all. The suppose let's do the base meshing. Okay, if we feel we need somewhere the refinement, we can come and refine, right? Let's do the by default whatever the mesh available, let's do the volume mesh generate out of the thing. So before that, let's check if skewness and other quality for the surface mesh is correct or not. Do it here. Diagnostic connectivity quality, let's go to quality, measure skewness around 0.7 mark. 83 elements are there whose skewness value is more than 0.7. How to solve those things? Let's go to the first element. Okay, these are the elements. These are very skewed, means these are showing these are some small element. Okay, how to resolve this? So there are a lot of ways. Either you can collapse those things, you can remesh those things, you can do the Delaunay swapping of those things. Let's select it. I hope with the remeshing these things will be go away. This button is my remeshing button. Okay, so let's go to the over here. Okay, Rings means it's select the neighboring cells. Okay, one, give some feature angle 40 or something. Let's see mesh. If see the problem is going on. Yeah. So now mark out of 83, the bad elements are gone away. Only 22 elements are there. Let's check so fast. Again, the same problem. Okay. We can do the remeshing over here to get rid of the bad element. Now this is also gone away. 13. This is we can also do remesh. Next. Here also we can do remesh. Mark. Now see, all the bad elements gone away. Let's check what is the summary. The highest skewness is around 0.67, which is acceptable, right? And total mesh count is how much? This is around 1,10,884, right? So this is the surface mesh count. Okay, so let's reset, view it, fit to window. Okay, so now what we will do, we can do the volume meshing. What is the procedure of the volume meshing? So auto mesh. Okay, the geometry is pump sealed. Okay, so then we have to develop a prism layer for the turbulence. Okay, let's go scope, set, wall prism, some name I can give. First layer aspect, let's put it default 10, number of 5. It will be developed in the fluid region, grow only on wall. So just change it to selected phase zone and select which phase zone you want your prism to be grow, right? So you have a lot of thing. Okay, so you don't need it to inlet and outlet, you don't need a prism layer. But let's see which are the surface. Draw this surface. This is the wall of the casing. You need prism layer over here. That's fine. So this is the let's see which surface. This is the interface between the MRF and the sliding mesh. Here you don't need any prism layer, right? This is again a solid surface, blade surface, where you need the prism layer. So let's select inlet, outlet, this one. You select this only layer surface for the prism layer generation. So this is already there. Okay, growth option, you keep it first layer offset and you create the wall prism is created. Okay, now come to the element size. As I yesterday told, let's choose the poly element. Compute is a maximum cell size is expand 70 something. I will put it 5. Okay, maximum cell length volumetric. Then merge cell with the Jones region. Apply. Now go for the volume meshing. See. See, now volume meshing is done. The quality has been changed to inverse orthogonal quality. Let total 2,53,000. This is around poly cell is around 0.2 million. Okay, The total cell is created around zero point 0.4 million. There are something prism cell is around 0.2, 0.18 is the poly cell. Okay, for total around 0.4 million is the total cell created. Okay, so let's see how it looks like. Reset, draw all boundary. This is right now my pump that is meshed. Okay, this is the pump I want for the simulation. Okay, that is meshed. These are my inlet, outlet, and all. You can see how good the mesh is just by checking the summary. This is telling that 0.92 is the maximum inverse quality, but you need inverse quality less than zero point 0.9. It's for betterment. So how to do it to reduce if something more than 0.9? So let's go to the auto node movement. Okay, first you check if your volume mesh is okay or not, if there is some negative cell in it or not. To do that, just there is an option. Okay, repair negative volume cell. Then apply. It will search if there is some negative cell or not. Okay, your mesh is good. You have cleaned up it correctly, so there is no negative cell. Okay, fine. Then you need to find out, fix your quality measure. It's around inverse orthogonal quality by default. Okay, quality measure I put it 0.9 because I want the cells which are above 0.9 to be get corrected, the volume cell, right? So iteration you put it around 10. Okay, you just make it apply. Let's see auto node movement it will do. Okay, it already one cell is above 0.9. This has already did the auto node movement and corrected that one. Let's see the cell quality right now. Summary. Now no cell is above 0.9 because during the auto node movement I have what I did the node movement of the cell and make it corrected, so that the maximum inverse orthogonal quality is 0.88 and it is around 0.4 million cell for the pump, right? So now let's see individually, we can see how the MRF zone is looking like. Draw boundary. This is my MRF zone. I can set the sectional view. This is my surface mesh, how it looks like. If I want to see the volume mesh, draw cell layer. Okay, you can see I told you earlier what I just need my the prism layer across the solid region. So this is my casing is a solid region. So across the solid region I just need the prism layer. So you can see there is a prism layer across the solid. My blade is a solid region. Across the blade I have developed the prism layer. You can see over here by zooming. Okay, so across the blade, we can see the prism layers is developed, right? But I don't need any prism layer across the interface because it's a interface kind of thing across which I don't need it. So I just turn off the prism layer generation across the interface. Otherwise, it will generate unnecessary the mesh count. There is not much any effect. We are not going for the boundary correction or low Reynolds number modeling across the interface because it's a fluid interface, right? So now the mesh is done. The quality check is done. We can go there. One thing we can do it over for the convenience, we can rename the surfaces, right? So let's go the boundary, manage. There is something called a rename surface. Draw. Let's inlet, outlet already we have renamed. Blade is already renamed. Let's see which surface it is. Draw. This is our casing surface, right? So we can rename it over here. It will be easy for us in the Fluent to mark W. See, casing, apply. This is already there. Then see, this is which surface. Draw. This is the interface, MRF interface zone. Okay. So W. It will not. Yes. The MRF zone interface. That's why I give the interface apply. And these are the interior cell volumes. Okay. Means these are the faces. If you look, it will take time, I guess. It will hang or something because these are the cell faces. Okay. Let's draw. Oh, we fall in the trap. Okay, these are the okay. You can see these are the cell faces. Means the interior faces means what after volume meshing, each cell has a boundary. Okay, that is a cell boundary. These are those kind of faces. We don't need to remember. Sorry, rename those cell faces, right? So let's save it. Right, mesh. Okay. This is showing in the post convection pump scale meshes. Okay, this is saving. Now the mesh is saved. Okay, so the rename, everything is done. Reset the boundary, done. So now put it. Then we need to set the force convection condition, turbulent force convection condition, where we need to set it in the Fluent. So let's go to the Fluent solver. How we can go? Either if you need a parallel computation, okay, we don't need any visualization or something. So let's simply close the Fluent mesher. You can go over here, but I want to do it in the 2 or 3 parallel processor. So let's I am closing it over here. You can directly go by clicking this window. You can go there. Otherwise, you close it. Okay, because now you have to come out of the mesher. Your mesh is already prepared. You close it, then open the Fluent again. Then instead of meshing, go to the solution. Where you give the location of the directory where your mesh is located. My mesh is now located here, pump scale msh.gz. This is in the same folder, force convection. Okay, force convection. I just allow the solver to be three processor. Okay, let's put it 2 processor, otherwise it will be take too much of my RAM. Okay, force convection. If you have a GPU setup like NVIDIA GPU, you can choose it GPU, but normally with student version and all, go with the CPU. I don't know if you have a functionality for the GPU setup in your hardware or not. Otherwise, go for the CPU solver process. Double precision. Now this is the Fluent solver window. We have come out of the mesher and we have come to the solver window. Now file, read, mesh, right? This is pump scaled. Now the Fluent solver is reading the mesh, whatever the pump meshing and all we have generated over there, it is reading it. It is already Fluent solver already read those things. Okay, the next thing is that check the unit, right? Then go to the scale. Okay, check. Okay, this is showing a pump where 90 meter, 169 meter, because this problem arises when we create the geometry in the space claim. Okay, these are all in millimeter, right? But in while we are importing, we need to scale it. Otherwise, the Fluent solver is assume the unit in the meter, right? So do what? Mesh was created in, you just go select millimeter. Okay, mesh we have selected in millimeter, 2 mm, 5 mm, like that. Scale. Now it scale the thing. The correct unit count 0.1 meter, x minimum, x maximum is 0, x minimum is minus 0.1, y minimum. Now the geometry is scaled, right? Let's see, visualize a geometry display. Yeah, this is my pump. Okay, this is imported into the Fluent. Then here I need to solve it, right? So to before moving further to the setup, let's check the mesh quality over here, Fluent ones. So this will give you the mesh quality, means the maximum volume, minimum volume. Okay, the minimum volume minus 13, maximum volume 10 to the minus 7, total volume it will give the total volume of the fluid domain that is under consideration, face area, maximum area. You can do evaluate mesh quality over here. Okay, aspect ratio and everything, it is going, it is showing it's correct, nothing wrong. If something is wrong, it will give you warning over here. You can go back to your meshing and rectify those things. Now I think we have a good mesh to start the force convection setup. There is no warning from the Fluent solver side. Okay, let's go how to do the setup for the force convection. Go to general. Okay, we need to select a pressure based solver. So normally you have incompressible flow or the compressible flow, right? Compressible flow is a density is a strong function of temperature. For incompressible flow, density is not a strong function of pressure. Sorry. So that's why we put the pressure based segregated solver, okay, or the coupled solver. We go over a pressure, velocity formulation absolute. It's a steady state. Let's first solve the steady state, then we'll go for the transient state. Transient state takes more time. Gravity, we don't much matter over here because we don't have any elevation head or something. Gravity we can neglect. Then you come for model. We don't have any multi-page flow over here. We don't have energy, but the turbulence by default, the Fluent set up to k omega equation. Okay, so we need k omega. Okay, there are a lot of turbulence model in the Fluent, right? So either you can go for the inviscid, means you are solving some Euler equation, you have some laminar flow, you have then the turbulent. There is one equation, Spalart Alamar Ras. This is normally for the aerodynamics equation, SA equation. Otherwise, for the two equation model range, you have k epsilon, k omega, right? Transition, this is 3 equation. There is a 4 equation model. This is the 7 equation Reynolds stress model. Scale adaptive simulation, then the detached eddy simulation, large eddy simulation. Hopefully Professor Andy Chan will teach you all theory about all these things so in the subsequent theory classes. So for the rotational part or the turbomachinery, the k omega equation is the standard equation. Then k omega equation itself, just a second, one second. The k omega itself has several variants. The standard k omega meters, Gecko, BSLL, SST. So let's choose it, k omega SST. Select low Reynolds number correction, means if you have any, as I explained, viscous sublayer, you want to be resolved, you do the low Reynolds number correction. Curvature correction and the production limiter, this put it something default. These are the coefficients. Okay, once you derive the governing equation for k omega equation, you will find there are a lot of closure coefficient needed to model, because you will get some third order pressure strain velocity correlation, etc., for which you don't have any closure at the range level. So you have to model it means you have to assume it in terms of some gradient of the quantity, simple gradient diffusion or the hybrid gradient diffusion concept, generalized gradient diffusion concept. So then to assume it, you have for different models, you have different modeling parameters. Okay, these are some modeling parameters, and the by default Fluent set some default parameter. You can play with that one, but you need to be expertise on the subject to play with this parameter, to change this parameter as per the requirement. Otherwise, just leave it as default. Okay, now this is done. Radiation is off, heat exchanger off, space is off. Now this model is done, right? So then other things you don't need it. Now model setup is done. Now what we need material. Okay, it's a fluid domain by default. Okay, it is assuming it's as air, but suppose we are pumping the water over here. Just go fluid material. So fluid mixture, fluid database. You have a lot of that material over here in fluid database. Let's solve water H2O or something, it will come. Water, it will be H2O. Where is the water? Chemical formula. And fluid database. Name water. W, yeah, water liquid, water vapor. So we need a liquid form of water. So select H2O. So once we selected, it will copy. Okay, close. Now see the density of the water and the viscosity of the water is available in the fluid properties. You can see it over here. Okay, it is water liquid. Okay, density is around 998 in the standard condition, or you can take it 1000, whatever you like. Then the viscosity is 0.001. Shell zone condition. This is important. This is where you need. How many zones you have here? You have two zones. One is the casing, one is the MRF. There is nothing to do in the casing. Okay. There is nothing to do in the casing. Okay. So just leave it over here. Check which material it is. Okay. So it is water. Just check it to water liquid, the material name. Apply. In the casing, you have the water. There is no air, because by default when Fluent has a property air, we have created a material database for water. We need it to be simulated. In the casing, you choose it water liquid. That's all. But in the MRF zone, you have to do a lot of things. First thing, just choose it property, which is the material. It's a liquid water. You choose it. Okay. Then there is an option called frame motion and mesh motion. Okay, this frame motion, mesh motion, both used for this moving the body, just like a blade or the gas turbine simulation. The frame motion is somehow selected for the steady state approach, which is otherwise known as MRF, moving reference frame. The mesh motion is something known as sliding mesh. Okay, this is used as a transient. We'll gradually go to this one. This takes time. Okay, to the do the computation. Let's start with the frame motion. Okay, then what will it is, you are starting the frame motion. What it is asking you? It is asking you the rotation axis. Okay, rotation speed, rotation information. Where you will get this rotation axis information? Okay, rotation axis origin, rotation axis direction. You need to provide us, and speed. Okay, to give the speed, it's normally by default is radian per second. Okay, I just want my pump is rotating 2000 rpm. Okay, there is an option over here, units. Okay, let's go to here. There is some angular velocity. The unit is radian per second. If I want to revolution per minute or rpm, I can change it. So by default Fluent will do what? whatever input you give it over here, this will multiply by a factor and convert it into SI unit. Okay, now see my revolution is my speed is revolution per minute. I can assume, sorry, I can give it around 2000 RPM. The pump is rotating, right? Then the rotation axis origin and the rotation axis direction. Where to give it? So let's come to the space claim. Okay, let's see here. My pump is rotating around what? Which axis? X axis. Okay, if it is not X axis, if it is some random axis or inclined some axis, how to know that? Generate it. So there is an option over here, axis. Okay, go over there, select the geometry, it will generate an axis for you. Okay, you again watch it, just go and select the moving reference frame. Okay, select the body. Okay, option is axis. The axis is generated for them. The MRF, the moving reference frame, is rotating across this axis, right? So to know the axis information, what you will do, go and select the axis, one axis, it will show you the axis information. So this is around X axis, right? If it in a random axis, it will show you the direction cosine for that one. You can put it, but it's in X axis, means X1. Okay, one axis. Just put it, come to the Fluent. Rotation, axis direction, it is rotating around X axis, X1, Y0, Z0. Otherwise, you have a, if it is an inclined kind of surface, you will get the axis information by G 0.5, 0.5 like that. Direction cosine you will get it, but it is rotating around X axis. That's why I put it X1, Y0, Z0, right? Then the rotation axis origin, where it is rotating, right? To do that, again, come to somewhere here. Okay, create some point in the plane. The origin in the x-axis doesn't matter, but the origin with respect to y and z matter, because while calculating the centrifugal force, it will ask with respect to origin, this will be calculated r omega position vector. Okay, to do that, what you need to do, we need to create a point and measure its coordinate. Okay, just select the surface, go for sketching. This is the normalized view. You can create a point over here, point, put the point over here. Okay, point is created. Now switch off everything. Okay, the one point is created. You need the point origin, so select it. This is giving you the point origin, x, y, z. Okay, this is in millimeter. Y is equal to 0, z is equal to 0, x has some finite value. So means if it's a good point, the axis is set to y0, z0 for the center. Otherwise, if it has some finite value, copy that coordinate value to here. Let's see. This is x0, y0, z0, y0, z0, and x is in millimeter. To convert it into meter, what you need to do? You need to provide divide it with 1,000. This is around minus 0.1188. Okay, x is around minus 0.1188. This is my coordinate is done. Minus 0.1188 y0 z0 minus 0.1188 y0 z0, 2000 rpm. This is rotating around x-axis 0, 0. Okay, I don't have any translational velocity over here. Okay, relative to cell zone, there is no UDF for the zone motion. Okay, so now apply. Okay, now what you do by choosing the MRF, you assume, means provide the velocity and tell the solver this is the non-inertial frame, make it inertial by applying centrifugal force and all. To applying that, you have already given the axis information, the coordinate information. center coordinate information and a rotational speed, right? So now that is done. Let's come to the boundary condition. What are the boundary condition over here? Pressure inlet and pressure outlet. Okay. To do that, let's come. So by default, we have not given any boundary type in the Fluent, right? So far, the Fluent is assumed everything to be of wall type. That's why it is showing the wall type. But here, what the boundary condition? We need a pressure inlet. Inlet, we have some pressure. Let it from atmospheric pressure. It is shocking. Okay. So just BC inlet. You just go there, click, change the type. Type. I just need it's a pressure inlet. Okay, so what is the total gauge pressure? Suppose it is sucking from the atmospheric pressure. So 10 to the power 1, 2, 3, 4, 5. Okay, this is atmospheric pressure from which it is sucking 1, 2, 3, 4, 5. This is the flow is sucking from the atmospheric pressure at 1 bar. Okay, close. Then there is a pressure outlet. Okay, type pressure outlet. So at what pressure it is discharging? Suppose it is discharging your head to somehow 2 bar or 3 bar. Let it be 3 bar. 1, 2, 3, 4, 5. Okay. It is shocking from 1 bar and discharging the fluid to 3 bar. Okay. 1, 2, 3, 4, 5. Right? Or this data you can give it as per your input. These are normally the input, right? Pressure, equilibrium, pressure profile, these are by default. So let's set around 10 to 3 bar. It is discharging the fluid. So now if you go there, see group by zone type. Now you see inlet, outlet, these are the internal, interior. Then wall, okay. So the interface, right? The interface, whatever we have created, interface the of the this is the interface, okay, between the MRF zone and the casing, right? By default, this is a wall type. Make sure to assign it interior, okay, not wall. So just select here type. Okay, just make it interior, means it will allow, once you define it interior, means it allow the transportation of the governing equation, momentum, energy, whatever, through the thing. Otherwise it will assume a no slip condition at the interface, but that's what we don't need it. Make it interior. Done. Very good. So now we have internal phase. So it's showing the interface of the MRF. Okay. Outlet, we have pressure outlet, we have inlet, pressure inlet. These are the blade and the casing. These are the solid surfaces. Right. So now we did the boundary condition setup. So there is a cell joint condition. Okay. So there is operating pressure. Okay, we don't have anything to do with the gravity and all. Operating pressure, this is something, your whatever value you have provided, that is in gauge pressure. Okay, for the absolute pressure calculation, your input gauge pressure is added with the operating pressure to calculate the absolute pressure. If you need your flow to be from pump from 1 bar absolute pressure to 3 bar absolute pressure, put the operating pressure 0, right? This is operating pressure is provided to minimize the numerical error by providing suitable operating condition. Make it 0. For incompressible flow, it is not much thing, but constant density flow. So in the buoyancy Rayleigh-Bénard convection, next example, we can see the use of operating pressure. Here it make it 0. Now it is done. The physics is somehow the setup, boundary condition, the cell joint condition, the method. So by default, Fluent assume coupled. Okay. For simplicity, you can use just a simple algorithm. So you might have already gone through this different CFD algorithm. These are the segregated algorithm developed by Patankar. Simple C. Okay. And this coupled deal means instead of solving the pressure, first guessing the velocity, solving the pressure Poisson equation by iterative manner, in the same matrix at a time the pressure and the velocity everything is taken. That's why it's a bit expensive, but it's very good for some simulation, just like natural convection where the density, we assume something, then you solve the governing equation for the momentum, then again we'll go for check the pressure by solving the pressure Poisson equation, which satisfy the mass continuity equation or the divergence field. But we can also assume it's a coupled algorithm or simple algorithm. Let's here we don't have much variation in density, etc. Let's take it simple algorithm, no issue. Then the gradient computation, there are a lot of algorithm. Put it least square Selbes, momentum upwinding. This is the upwinding scheme. You might have known about the upwinding effect. Means this is somehow the property of the transportation of the Navier-Stokes equation that needs to be upwinded. Means directionally on earth it has to be provided. So momentum, we put it second order upwind. The turbulent kinetic energy, etc., put it first order, because as the solution proceeds, you can make it second order upwind. Sometimes the higher order upwind initially result divergence of the solution. So put it first order upwind. Okay, and the simple algorithm. Okay, then control. These are the under relaxation parameter. Means this parameter URF factor you need for the convergence of the solution, control the convergence. Something pressure you reduce it to 0.2, momentum you reduce it to 0.5. This turbulent kinetic energy and dissipation rate, something around 0.5, you don't need to change whatever viscosity. As the solution process with respect to the iteration, we can increase this value to accelerate the convergence, right? So now what is the output? The output is the mass flow rate, right? Within this pressure difference, you are rotating the pump, okay, and you want to see the how much fluid it is pumping with this much of rotation. Suppose you are developing a HQ curve with the pump or the blower. So what the head difference versus the flow rate you want to measure, right? So you put head or the pressure difference as an input. Now you need to find out your flow rate as an output. So there's a report definition. Okay, it is showing whatever quantity you are measuring to report this at particular end of time step or at end of iteration. You can report those things. Report definition, go new. Okay, surface report. What report you need? We need a mass flow rate. Okay, mass flow rate at which surface? We need mass flow rate at inlet, we need mass flow rate at outlet. Put per surface means it will calculate mass flow rate separately for inlet, it will calculate mass flow rate separately for the outlet, right? And report to file, print to plot, print to console, right? We don't need to save those things. If you put report to file, one additional text file will be created, and it will every iteration save your data. If you need it, something time dynamics of some quantity, how mass flow rate is changing or something, you can put it report to file, but we don't need it. We just need it plot it over the console. So just we put it print to console and report plot, and make sure to switch on this surface. So this, after switch on this surface, individually it will calculate for each surface, otherwise it will calculate the net effect. Just measure this file name, something mass flow. Okay, in out. My report file is now created. Okay, they are monitoring the residuals, etc., convergence. Okay, those are fine. So now coming to the calculation activities. Suppose I want my solution to be saved at particular iteration, right? I put it something around 50 iteration, 100 iteration, 500 iteration. Suppose you have to total do 1 lakh iteration simulation. So after every 1,000 iteration, you want to save a solution, because sometime maybe the solution diverges from a particular after a particular iteration. Sometimes your power failure, your computer stops. You don't want every time to start from the beginning. So if you save the intermediate solution, from the intermediate iteration itself you can start. Okay, then it is asking whether when it is saving the intermediate solution, the data file, if it can save the case file or not. So you choose whether to save the case file or not save the case file. Okay, so I there is not much change in the case file in this present case, so I uh, don't need any change. Then this return the most recent file, means how many files. Suppose you are saving at every 1,000 iteration. So if you have a 1 lakh iteration, it will save around 100 files, which unnecessarily increase your memory. Okay, the storage memory. To avoid that, maximum return only 2 or 3. Means when it is saving 3,000 iteration file, it will automatically delete the file having 1,000 iteration. When it is saving 5,000 iteration file, it will delete 3,000 iteration. Only 2 file will be saved. Remaining file automatically will be deleted. So just do that. Just put something underscore something, so that it will show the iteration number dot cache dot gz. Sorry, yeah, by default. Okay, you can give the path itself. Then run calculation. So number of iteration, I can put it over here 1,000. Okay? Or you maybe need more, 2,000, 5,000. This is again till the mass balance is going on. You can check it. Then first I need to initialize it. Then I need to run it. This is asking for hybrid initialization or standard initialization. I just go for standard initialization. Put everything to 0, 0. Have some finite value for turbulent kinetic energy and turbulent dissipation rate. So initialize. Now everything is initialized. You can see the turbulent viscosity, means eddy viscosity. This is around 0.1 million. Okay, in these cells, this is generated. Run calculation. Now see the beauty of CFD. We set up everything. Now we want to run the calculate. Now it started running the calculation. You can see over here the residuals. Okay, everything is converging quite nicely. Or there may be something wrong. It may be oscillate, zigzag, zigzag. It may be oscillate. Okay, so let it run for few 100 iteration. Then we can save it and check the intermediate result. You can now see the setup. Oh, I forget to save the cache file, because the good practice is after you did the setup, you can save the cache file. So for the safety, I'm saving it. Stop. You can do stop anytime. All the things are done. So I just need to set up it. Pump scaled or something, force convection. I just can save it. Let's set the case file, so that in case of any computer hang or something shut down, I can use the reopen that case file. Every time I don't need to set the condition again and again. Put it calculate. So in the meantime, it is calculating few hundred iteration. We can take some questions if required. So yes. So now we can take some question till the calculation is over and we do the post processing. So yes, please. Any questions?
Participants, if you have any questions, you can ask.
Because
Speaker.
this is the request I got from the email from someone who asked me to show him the setup for the blower or the pump.
So there is one question in the chat box.
Uh-huh.
Any critical points to be kept in mind?
Yeah. Any critical points to be kept in mind means what exactly mean by critical point? Can you, if you elaborate the question, you can switch on your video and come and ask. It will be good. Someone named Debraj K. He asked me for this problem of the fan blowers. Hope this answers his queries. The setup. Please feel free to ask in the voice by voice. So what exactly mean by the thing? Debraj, please switch on your camera and ask the question. I will answer it. What exactly your doubt is?
One second, sir. Let me unmute you, sir. Devrat, sir.
Sir, can you hear me?
Yes, I can hear you.
Yeah. No, my question is actually usually when you are trying to look into some kind of a turbulence, this thing, maybe the compressor problems are the most difficult one. Where we have different pressure ratios. Maybe if you take for a fan, we have a very low pressure ratio, and if you go for a maybe high pressure compressor, maybe something like an axial flow compressor or a centrifugal compressor, it will be a high pressure. So my question was with respect, can you able to show such kind of modeling, maybe from analysis perspective, where the turbulence aspect is also addressed, and you'll be able to show me how we can do it on the Fluent. That was my question.
Okay.
And my second thing is like now if I take for a compressor, if I change the working fluid from the air to water, maybe some of the design aspects are going to change. Maybe your blade shape or some of the things. So maybe those things also, how from the analysis perspective we can look into that. Maybe that also I want maybe some kind of an answer from.
Okay. Okay.
Yeah.
So
Compressible fluid as well as incompressible fluids. How we can look into that.
okay. So any other questions? Okay, Deborah, this is the thing. You asked a lot of things in between. So what I saw the setup process. This is going to be same. This is going to be same for all the compressor or the pump. Okay, the only thing you have a moving part. That's why you need a MRF zone. Okay, setup. How to set up the MRF zone? Already I have shown you already in the space claim how to segregate the blade and prepare the MRF zone, take its origin, axis, etc., and defining. Whether it's a pump or it's a compressor, it's the same, right? The working principle is same. Here, the pump, they push the fluid from the low pressure region to the high pressure region, while the compressor do the reverse thing, right? It compress the fluid. So the pump, the compressor, they're almost the same. They push the fluid naturally. If you allow the pipe kind of thing, you define a high pressure at one point, you have a low pressure at one point, the flow will start from the high pressure to low pressure. Here the flow direction is different. The flow starts from the low pressure region, it goes to the high pressure region because you have a rotational part. Inherently, the principle remains same. The compressor or the pump, so both low pressure to high pressure. And regarding the pressure ratio and all, yes, based upon the data, you can have set the boundary condition. Already I have shown you the boundary condition panel. You have the inlet, you have the outlet, pressure inlet. You can see the inlet pressure. Suppose you have a steam turbine cycle where inlet pressure is around 2 bar. You need to pump it to 10 bar or something high pressure boiler. So the outlet you can put the high pressure value, right? So 10 bar or something. That is the question. And second question is regarding your design of the turbulence parameter. So here we assume the K omega SST model for the rotation, because a lot of things by virtue of the thumb rule, it is already established. You can choose any other model if you want. You can fine tune the model parameter, but as the standard practice, some things are chosen by thumb rule, just like widely used model is K omega SST right now. Okay, yeah, 5 years back by default the Fluent setting were K epsilon model. So because of this turbo machinery part of rotation and all, K omega SST model is provides the good result, right? So we choose this model. So these are the requirements that means we take it as an inlet, just input, just like our boundary condition for inlet pressure and outlet. This turbulence model is something mathematical part. So based upon the available literature, based upon the available turbulence model, computational resources, we have to choose. If you have a high you want to see it high resolution, the result, the vortex, eddy formation and all, you can go for large eddy simulation. This is expensive, but if you want some average property like mass flow rate, etc., you can go for the RIAN simulation, right? And second, as far as your question regarding compressible and incompressible flow, I told you from the beginning that we have considered here the pressure based solver. So there are might means there are confusion between two things. There are two different entities. One is called compressible fluid and incompressible fluid, compressible flow and incompressible flow, right? So the compressible fluid and incompressible fluid, so they are different. Air is kind of compressible fluid, but water is a incompressible fluid, right? But if you come to the flow, as long as your flow Mach number is less than 0.3 or something, inertia to, I think, elastic force Mach number, the sound velocity of the flow to the velocity of the sound. Okay, all the flow are naturally incompressible in nature, right? If your Mach number is low, irrespective of fluid, whether you choose it air, whether you choose it water, if the Mach number is less than 0.3 or 0.33, around that range, it's incompressible. And physically what it is telling, the incompressibility is a condition where your density is not a strong function of pressure. There is, your density doesn't depend on your pressure, is a strong function, just like in the thermodynamics, you have a equation of state for your density, right? You have a, maybe your kinetic theory model, or you may be ideal gas model. P is equal to nRT, those relation where your density, okay, rho RT, rho is a function, strong function of the pressure. But for in the ideal normal condition or isothermal condition, your flow is not a strong function of pressure. So that's what you can tell, it's a incompressible flow. So here for the pump kind of application, whether you are pumping the air, you are pumping the water vapor, you are pumping the water, that doesn't matter much, because your density of the fluid is not much changing with respect to your pressure that is developed by the pump. So that's what the thing. So every flow here we can assume it's a incompressible. That's why we are have chosen the pressure based solver. But if you assume your density is also changing with respect to pressure, and then you can go for the density based solver, then you automatically your thermodynamics relation comes into consideration, not only pressure, not only density, then another parameter is the temperature. Means in your pump, if somewhere temperature is also varying, then based upon the pressure, temperature, density is also varying, you have to define additional complexity in that density based solver and solve the equation. Hope this answers your questions. Next question, please.
So there is one more question posted. How do we model free surface flow?
Okay, okay, I will come to answer this question. During solving the natural convection, I will show it how to model the free surface flow. Good question. So basically, when you have an external flow, right? So just flow across a cylinder or something. So you if far away from the solid body or the cylinder surface or any wall, so you have the velocity field which is symmetric. The symmetric condition is nothing but the region where your velocity gradient vanishes, the normal direction of the gradient vanishes, means it's showing that there is not much effect of the shear in those regions. So artificially in the computational purpose, we don't take a infinite region. For mathematical analysis, people assume, okay, this direction from minus infinite to plus infinite, but in computational purpose, we have to select some finite dimension. So that's what we almost 10 times or 12 times from the size of the geometry. Suppose it's a cylinder or it's a sphere, 10 times or 8 times the diameter of the cylinder or sphere. We have taken a region and create a closed geometry, because for the CFD simulation we need a water type geometry, and those boundary, instead of the wall, we put it symmetric condition, so that the velocity gradient is zero over there. Instead of a finite velocity, we have a gradient defined zero at there. So it's a symmetric boundary condition. By putting symmetric boundary condition, we just give the free shear flow, free surface kind of thing. I'll show you. I'll show you those things, just like a flow across a cylinder kind of thing. How to do that? I'll show you next. Next session, I'll show you. While solving the natural convection, I'll show you. So, like this is boundary condition or something more question, I can see a lot of things.
Excuse me, sir.
Yes, yes.
One more participant has raised a hand.
Mm-hmm.
Venkatesh, sir, you can ask. Yes, sir.
I think he's muted. You are in mute. You can unmute yourself. No, I cannot be able to hear you. You are not audible.
Yes, sir. Sir, one problem as such in biogas, no, sir. For on biogas combustion part, we have many tutorials and literature on CFD simulation part.
Okay.
But for biogas production part, no, the initial phase of it, one biggest issue is hydraulic retention time. So that hydraulic retention time is a function of temperature. So is there any tutorial kind of thing in your model, so that that hole with the various temperature, how that the retention time can be reduced, that can be simulated through CFD? That is one part. And parallelly, this mixing is another issue in this to maintain a same homogeneous phase of this slurry. So is there any such kind of simulations you have with you, or if you have any idea, please share, sir.
Yeah, Venkatesh, to be honest, I don't have any idea about the biogas exactly, except the researcher. No one else in the universe know what's exactly going on. So I don't know what's the research problem. It needs much more effort to learn the research problem and make the statement. Here, the purpose of teaching is something generic. So if you are very specific to a problem, so I have to look it before make some comment. But again, the thing is that yes, many things can be done on CFD. So it's upon the analyst what things you need to be done. Just like you told, you need a mixing. So in that case, you need a stirrer or rotational device, because it facilitates the mixing kind of thing, right? Easily. So retention time and all, I don't understand what exactly by retention time. You are telling some property you need that changes with time. You unmute yourself. No, no, not audible. I think host muted. So host can unmute your. Madam, please unmute her. Unmute him.
Yes, sir. So the point is, whatever slurry we have, no, as usual, naturally, let us take the cow dung and water as a slurry for biogas generation. There are many inputs for that. The point for that, no, to get proper biogas, at least it requires 30-35 days. So that is called retention time. In order to digest whole this, no, convert that slurry into biogas, it will take 30-35 days, sir. But if we can maintain ambient temperature, so that retention time, the conversion of the slurry into the biogas, it reduces the timing of the at least half of the actual time required, and that is the biggest challenge right now in that field, the research area. So is there any model kind of thing so that we can simulate to optimize this initially in CFD, so later we can do it an experimentation part? That was the thing, sir.
Not any idea, because the purpose is here much generic. So your question is much specific to a research problem. So I have to look detail into it, what exactly the problem statement and all. So to make an assessment about the CFD simulation. So sorry,
Okay.
I don't
Thank you,
have
sir.
any pinpoint answer to your query at this time.
No problem, sir. Thank you. I can contact you later, might be. Okay.
Sure, you're
Okay.
welcome.
Thank you, sir. Thank you.
Any other queries? I can see the chat window. So if you can give the Gayatri madam, if you can give the mic to the participant who had put some message in the chat window, we can take
Any
that.
other doubts from the participant side?
Not any doubt?
Okay.
Okay. Nice. So let's come to the thing. Let's see. So it's around 700 or 800 simulation is done, but still it is a reverse flow, means the simulation is not established yet. Some reverse flow is going on. Once the simulation is perfect, this reverse flow will go away. Okay, this is initially part of the solution. Okay, so let's stop it here, because we have to spend a long time to complete the simulation and see the results. So might be I will transfer the geometry to you. Might be you can run it. You can see the result for a long time. Okay. I will teach you how to post process, how to see the result here, and what is the sliding mesh approach over here. So, and I will transfer the file to Gayatri madam. She can share this with you. You can run it for a long time and see. You can prepare the animation or any profile like that. Okay. So this is the flow it is coming, and it is the flow it is going. So this needs to be perfectly balanced. It is now there, but it's a reverse flow kind of thing, right? So let's go graphics, contour. Okay. What I need to see? I need to see the velocity at the blade. Okay. If I am doing a centrifugal pump, V is equal to R omega. This is the first thing to be verified in terms of the rotation kind of thing. You see, Now the gradually the velocity is developing. Okay, so you can see it from here. So it needs some time to set up. You will go from gradually minimum velocity here to maximum velocity here, minimum somewhere here. So here to here it is going. So you can see it, the tip of the thing, you have the maximum velocity. So this will come. This is solution is not yet perfect. This just started. So once the solution will be final, you can see those kind of thing over here. So this is kind of thing contour, velocity contour. You can see the behavior over the thing. So these are the volumetric region actually. Okay, if you want to see any volumetric flow over here, you can see it, right? So otherwise you can take a cross section, you can also see that thing. So you can take a sectional view, you can see the things. So already I have the simulated result. So it takes a long time to complete it. You can see how it is doing. You can do the thing. Here it is a sliding mesh. I will show you, inform you what is sliding mesh. So next you can see the thing. You can prepare it, how it is rotating and flow is generating. It takes a long time to record those things. Okay, this is sectional view. You can simulate it. You can see the pressure field. You can see the mass delivered, etc. So normally, so what will happen? So there is a lot of challenge actually here. While solving it in the okay. MRF approach, this is a steady state approach. We assume our blade position to be fixed with respect to time, right? So it always may not be a correct approach. It may not always give the correct flow velocity. Okay, sorry, mass flow rate, etc. Because the blade is continuously rotating with the time. If there is not sufficiently number of blades uh, in the rotor, right? So here almost 3 uh, 4 5 6 7 8 blades are there, so it's kind of thing. But sometimes it comes with 3 or 4 blade rotor. So in that case, if you are solving the problem with MRF, because MRF is computationally efficient compared to the sliding mesh, it takes less time. That's why we prefer it. So what will happen in the geometry itself? We just rotate the blade. Now it is in a position. I can rotate it from here. If I go there, there is option called move. Okay, so I can move it angular, move along this axis or something. I can provide it the body which I want to move it. So this is the body I want to move it. Okay, so the move in the angular direction, I can move it here. It's asking me angle. Suppose I can move it another 15 degree. Okay, it's rotated 15 degree. You can see it is rotated 15 degree. Control Z, I'm doing it again. This blade is right now here. Put it. I just want to move it. Let it 30 degree. Now the blade is rotated 30 degree. So whenever I am creating the mesh, so normally we need 4-5 position of the blade. We fix it, generate the mass flow rate, then if we make the average, it usually gives us the good approximation of the mass flow rate, because the blade is rotating in physical sense, but Here for computationally effectiveness, we assume the static position of the blade and rotating a fluid across it. If there is not sufficiently higher number of blade, if you have a 20, 30 blade, that's fine, because even if rotated 20 degree, 30 degree, it is going to be isometric kind of thing, rotational symmetry kind of thing. But if you have a 3 blade, 4 blade, 5 blade, so in that case, if you are taking the MRF flow field with respect to a particular position, then you either under predict the flow or over determine the flow, right? To avoid such things, normally we do the 4, 5, 6 different positioning of the blade, save the different meshes and save it, then do the statistical averaging for different position to get the mean flow rate. This is one approximation flow where we solve it in a steady state, right? But again, we have a huge computational resource. I have a cluster computer, or I have access to ISC or somewhere supercomputer where I can run it. So so in that case, I can go for the transient simulation. Means instead of here in the geometry itself changing the blade, I will allow the blade to be rotate, the mesh to be rotated in the solver itself, right? So that kind of simulation is called sliding mesh simulation, where the mesh actually slides physically in the solver, right? And when it slides, the non-conformal interface created, right? When we'll go over here, the MRF zone between this and this, as the zone moves, the non-conformal interface will be generated. Okay, the blue region you are seeing, the non-conformal meshes will be generated over here. That is called the sliding mesh approach. How to do that? Suppose now the best idea is to do the meshing for the thing, bring it over here in the MRF, run few iterations, so that sliding mesh initially you may get divergence or something. So but to avoid that one, to do the MRF simulation, bring your mesh over here, set up the MRF simulation, run it for few thousand iterations, you have some good results. Now for accuracy you can move to the transient simulation, right? Let's save the data. I think data is saved for some number of iterations. General, you go over here, you choose it over here, transient simulation, right? In the transient simulation, now where to give the sliding mesh, you can go in the zone condition, right? This is a cell zone condition, this is the MRF zone, right? Then this is called mesh motion. Copy frame motion to mesh motion, copy to mesh motion. Now mesh motion means mesh is now rotating. Every value over here, they are copied over to the mesh motion, right? Apply now. But as I told, they are going to be form what? Non-conformal meshes across the MRF interface. So you need to modify in the mesh level. Okay, how to do that thing? So first go to the mesh. In the, this is called TUI window, text user interface window, right? If you go there, a lot of options are available. One is mesh, adjoin, define, lot of things are there. So just go to the mesh, copy it. You can see whatever the other option available option in the mesh. Okay, there is something called zone modification, adjacent check, memory, modify zones, right? Modify zones, mesh modify zones. Then in the mesh modify zones, it is asking a lot of other things. Modify zones, active cell zone, adapt mesh, append mesh data, a lot of things. Just MRF to sliding mesh. There is an option called MRF to sliding mesh. Okay, select that thing, copy, MRF to sliding mesh. Then it is asking for the zone ID, because whatever the ID you are generating, name you are giving, when you are bringing it to Fluent enumerate it. Means enumerate means it assign all the name to a particular number, right? If you look at here, it for the caching fluid, it automatically given a number 1251. For the MRF zone, it has given a number 1248, right? Similarly, for boundary condition, boundary, it has given a number 4 to 1247. This is somehow Fluent generate from the solver generate. You don't need to explicitly give the name for it. You can give the number for it. You give the name, Fluent will generate the number, right? Here it has generated a number for the MRF. You can see it display. Okay, this is the zone you need to convert into sliding motion, right? It has a number 1248. So bring that number, give that number here, 1248. Okay, zone 2 MRF doesn't have a MRF as motion specification, right? Now I think it's already there, that's why it is showing. So the sliding mesh is there. Let's see, run it. What's the problem it is giving? Let's see. This is the normally the procedure. So you have to give the cell zone name or the ID. Let's take the ID 1248 is to MRF. Doesn't have MRF as motion specification. So what exactly it is telling, motion specification, why this error is giving? Because already we have copied the setup over here. Okay, if you go to the frame motion, now it is in okay, so now it is in frame motion, it is in MRF zone, right? Now I need to modify zone to make it sliding mesh, because now I just already we are in the mesh motion frame, so that's why it was throwing some error, right? So now at the end of the MRF simulation, you have something like this: frame motion, relative adjacency, rotation axis, rotation direction, everything is same. Apply. Now let's come and do it. Mesh. MRF to sliding mesh. It again asking for the ID. You put it 1248. Now you check. It automatically convert the MRF to the sliding zone. So you can see over here. So the frame motion is now mesh motion. Apply. Okay, the interface is now created. If you look, two interfaces is now created. The sliding interface is now created. The first thing you need to do it over here. Auto save every, then associated case file each time. Otherwise, what will happen? With time step, your mesh will be changes. But if you are not saving whatever the data you are saving in the folder, that you cannot read it with the initial case file. So every time you need to save a case and data file. So okay, that's okay, invalid character, something is wrong. Okay. Some error is giving, so because for a researcher, error is a thing. This is number of time steps. Suppose for 10 I given, okay, and 0.001 I put. Okay, now the question is, what is the time step size, right? So when you are doing the transient simulation, keep in mind you have to choose your time step such a way that at each time step the pump maximum rotates 15 to 20 degree. Okay, so it's rotating around 2000 rpm. Then you can calculate the per second how much is the angular motion. Okay, radian per second. You take a delta t such a way that maximum 15 to 20 degree the pump is moving in the particular time step. Otherwise you will get a bad result and sometimes divergence of result, right? You can do this tutorial, means pen and paper work, calculate the delta t such that if 2000 is a rpm, it is rotating, convert the delta t required to rotate around 15 to 20 degree, right? So after all those things, again calculate. Let's see. Now it is a transient simulation. You can see it will take time, but again it will be a transient simulation. Now till now we are doing a steady simulation. Now it's a transient simulation. Now the blade profile is actually rotating in the mesh itself. Earlier it was a static mesh. Now the blade profile is itself rotating in the mesh itself. Here you cannot able to see anything here because whatever the thing here we are seeing with the flow time. So not iteration. Earlier it was iteration. So once the one time step is over, the data will be populated over here. See, 1, 0. Yeah, data is populated like that. For each time step, it will do 20 around iteration. Then at the end of each iteration, it will populate some data. So the best practice is first, whether it's a pump, it's a compressor, first do the steady state simulation, get some converge result, then go for the sliding mesh and then started the transient simulation from the steady state data. Otherwise, if you start something from the zero, it takes a long time in the transient simulation to get a converged profile. Okay, so hopefully it is going to take a lot of time. So I am going to transfer this case setup file to Gayatri madam. So she can share it with you. You can practice your own. If you have any own design of pump, blower, that also you bring it over here, mesh it. You can do the simulation. You need a very good computational facility. Then you can have your result. So that's all. I think that's all for the this session for this force convection. Next session will come for the natural convection. So let me figure out the workbench meshing because I have a double monitor in office. So somehow this workbench is visible in the other monitor. In the single display, it is somehow getting hidden. So next session I will give you some tips regarding the workbench meshing. Then I will again tell you how to do the natural convection setup in the Fluent, just like Rayleigh-Bernard turbulent Rayleigh-Bernard convection. So we can do it in the next session. So this session, I think already we are over of time. So I'll open the session for few questions. If we have done, then we can close this session.
Thank you, sir. What is this?
Any more questions?
Any questions from participant side?
Hello. Sir,
If no question, yes.
sir.
Any
natural
questions?
convection- Yes, ma'am. For natural convection, no. If it is possible to demonstrate with a simple problem with geometric modeling, possible with a simple problem.
Who is asking? Can you please
This is
unmute or video or?
This is Dr. Venkatesh Lamani from BMS College.
Okay.
We can if we can start the demonstration with a simple problem like a flat plate, geometric modeling and meshing, it will be going to help more, sir.
Yeah. Earlier I got the request from Chandrasekhar to show the Rayleigh-Bernard convection. So the simple cavity already I day before yesterday. The first day I just prepared a simple cavity in the space plane. I guess you are there in the session.
Yes, sir. Okay, same problem you're going to
that cavity we already yesterday we generated the polymesh. again, we can, if you requesting, we can again today do the meshing in that cavity so that it will be a practice session, memorizing session for you. So
Yes,
you can go through again the meshing in the Fluent Mesher for the cavity meshing. Then we'll set up the natural convection. Yes.
Fine, sir. Thank you.
Any other questions? Okay. If no questions, please turn on your cameras for photo. Thank you, sir. It's done.
Okay. Then
Yes,
after, I think
we'll
after
meet
30
after
minutes.
1 hour. Yes, sir. We'll meet after 1 hour at 2:15 for the next session.
At what time?
2:15 Indian time, sir.
Okay, we are already extending the time. It was earlier 2, right?
After 1 hour, sir.
Means, what is the current time right now? It's around, I guess, 1:30, right?
Yes, sir.
Okay, 2:30 we'll meet it again.
Okay, sir. Okay.
Or what time? 2:30
We'll
or 2?
2:30, sir.
Okay, okay. Let's have a
We'll
1 hour break.
we'll
So,
come back. Yes, sir. 2:30 we'll meet it again.
yeah, please text me the
2:30
exact
to
time.
4 o'clock.
Okay, okay. Thank you, everyone. Hopefully, you enjoyed the session. So, see you in the next session.
Okay, sir. Thank you, sir.